And we're going to thank Manci again. And the next speaker is Massimo Caccia, that's going to describe another detector proposal. And we hope to have more time for discussion later.
Looks like working, yes. Okay, so the idea detector concept has been introduced already a few times, and here I just want to detail it a bit. And there will not be so much of physics, there will be a little bit of detector physics and the main motivations for the choices that we made. And one of the choices is that actually I'm part of the ILD, so I know the ILD by heart. And I've been investing a lot of time in the definition of the idea. So we all thought that it would have been nice actually to consider something else and to have a comparison. So again, step by step, I'm moving inside out. Let's see which are the choices and the challenges that we have to face. And of course, we have to start by the vertex detector. And as I said at AKUST, when I was invited to give a summary, the essence of building up a vertex detector for this sort of experiment is actually to fit 1 billion pixels in a diode code CAN and to keep it cold. This is what you have to do. And you know that actually the challenge is absolutely not trivial because, again, both for the circular machine and for the IRC, the request that you have on the input parameter resolution is such that the asymptotic term has to be at the 5 micron level. And then you want to see also the multiple scattering term, which is actually the level of 10 micron. And then you have to scale it down by the transverse momentum. What does it mean in terms of constraints on the detector? That if you're sitting the closer layer to 60 millimeter and the outer layer at 60 millimeter, you need to have a single point resolution at the level of 3 micron. That we know is actually something that we can achieve today, but the constraints, and you will see later that you have to fit, are such that are making the exercise absolutely not trivial. Now, if you look at this constraint, this is turning into thickness per layer, which is 0.15% of X0, which, again, if you turn it into pure silicon thickness, is not horrible, but then you have to consider that even if the vertex detector is small, you have to keep it together. So also the structure, also the fact that you have to keep all the layers in places, is telling you that this is something that you have to take into account seriously, especially and notably because this will be significantly affected by the power dissipation that you have in the cooling system. So again, I mean, all of the pieces have to fit together. Now, then you have to consider the time structure of the beams. And there, I believe that the challenge here is a lot more serious with respect to the ILC, especially for 2 main reasons. The first one is that the time structure is such that you have equally spaced collisions, while the main advantages that we had at the IRC were due to the, say, anomalous or finite time structure that was allowing us to have the power pulsing that, of course, is offering you a significant advantage. And then the other question is that you have to be able to cope with a sweeping energy from the giga-Z to the Higgs sector, and then again, the beam crossover that you have because of the extremely high luminosity is such, then again, you can go down to 25 or 50 nanoseconds between the bunch crossing. And then if on the high energy side, you will be working essentially triggerless, of course. This is not something that you have to do when you are a giga-Z. So again, to have the flexibility into the architecture to cope with all of the different boundary conditions make a lot of sense. Then again, the expected beam-induced background is something that you have not to neglect. So yesterday, well, the day before yesterday, I had a number here that was essentially a factor 20 higher. So I'm happy that Hongbo and other people there, I had numbers that were 2017 Beijing. I changed them to 2018 Roma, and I'm happy to see that there was a final focusing that has been reshaped in such a way that the background dropped by a factor 20 in 1 year. But again, this is something you have to take seriously into account when you design the detector because the occupancy has an impact. It has an impact on the granularity. It has an impact on the pattern recognition. It has an impact on all of the different details of the vertex detector. Now, as far as the expected radiation level, at least you can relax. Now, what are we dreaming of? I tell you what I'm dreaming of. I'm dreaming of a binary detector. That is to say, where for every hit cell, I just say whether it's black or white, and I'm not very much concerned about the energy deposition, because I know that if I can go binary, then I can anyway get to the 3.5 micron resolution that I need, and I know that actually the power dissipation can be a lot smaller, and so I know that it will be a lot easier actually to fit into the constraint about the power dissipation that I have. And again, this has been proven by the Strasbourg team. But again, look at the red number here. This is definitely too much. So if you're going to go for something like this, then you will not have the possibility to cool by air. And this will, in turn, have an impact on the material that you're going to have inside. So again, this is, for me, a very key issue. Then again, the other wish that I have is that I don't want to have anything which is parallel column readout. I think time has come where the technology is offering you the possibility to have on-pixel spacification, and then either you go with a token ring architecture or anything more sophisticated, but we know that actually, even if the readout time is somehow connected to the occupancy that you have, and you go back to slide 1, this is the way to go because of the flexibility that you have. So here, the reference is actually Alpide, so what has been done for Alice. But even so, you can see again the red number here, which is my nightmare, is dissipating too much. Now, what we also know is that there's a lot of experience within our community in commissioning systems. So also system aspects have been already faced and tackled. And of course, the very beginning was the star sensor. And the big stuff is what is being constructed here for Alice, where you're going to have 7 layers, 10 square meters of monolithic active pixel sensors. And you see the outer layer is 43 centimeters. So you can really be brave. You can imagine to go from, say, a core of vertex detector based on pixel to a seed of tracker, which is based on pixels, which is interesting. Now, and again, as I would say in my final slide, say time is on our side. So we know that actually we have a lot of experience in the community, but we have to be brave or at least bold, and we have to see what new is on the market. And for instance, there is this very, very nice activity which has been proposed by INFN. It's called Silicon with Embedded Electronics Development, where the next step is to take the best that you can have from the monolithic approach together with the best that you can have from the hybrid approach, which is essentially the fact that the full silicon layer is actually depleted. So this is like integrating the electronics on a high resistivity substrate. There you have now wafers that are allowing you to do so. You have technologies that are open. You have the TowerJS, you have the L Foundry, you have a few people here and there. So I believe this is certainly something which is worth being concerned, because you go from the 15 micron thickness layer to 300. And so you go from 1,000 electron to 24,000 electron signals. And of course, what you have to win is definitely tremendous. So it's very, very interesting, at least to me, also for many other aspects. Now, vertex detector, just my first conclusion, is that, again, we know how to do it. We know that we have to improve. We know that actually the key issue will be to be able to identify an architecture and to have to identify a technology which is allowing you to dissipate less than 20 milliwatt per centimeter square. This is the limit. If we get there, then we know that a gentle air blow will keep it cool, and then we know that then the mass will be small, and then we know that we can fit all of the constraints that we may have. Now, one more step. When we go to tracking system, we know that actually there are different ways to draw an IS-3. There are different ways to try to reconstruct the same event. We know that if we go this way, that is a full silicon tracker, then we know we have some advantages. But again, well, even if we know there is something that doesn't meet the eye, this is very, very tempting. And there are situations where actually the choice is somehow mandatory, because what you have to consider is that, again, here, and this is different with respect to the ILC, we unfortunately, or say, we cannot cope with very high magnetic field. And if we cannot have 4 Tesla or even 5 Tesla, then we know that actually the radius has to be large. And if the radius has to be large, it's very difficult, irrespective from what Alice did, to get up to, say, 4 meters with silicon. This is a bit too much. And again, the main motivation for keeping the radius large is twofold. Say, for calorimetry, we know that actually the name of the game is actually to be able to separate the showers that are associated to neutral particles to the showers that are associated to the bending charge particles. This is what you want. And again, you can plug in the numbers here. Here, if you do it in meters, you will get meter. Then here you do it in JeV. And if I did the exercise again yesterday, and you see that if you plug in 2 Tesla and you're sitting at 2 meters, you have this separation, which is something like 120 centimeter over P. So for 10 GeV particles, it's 12 centimeter, and you know that you're already in troubles. Because at least for the hadronic particles, the development is 1 lambda. 1 lambda is typically 15 centimeter or so, and then you're really to the limit. So you cannot actually get smaller than 2 meters, or even, say, 4 would be better. Now, again, why R is important? You see it here, because we know that with respect to LEP, again, we want to get 1 order of magnitude better in the curvature reconstruction. And again, what you have to consider is that you have to be light. This is the multiple scattering term. You have to have a reasonable number of points that are very precise, and again, is scaled at 1 over r squared. So you have to be a large radii. You have to have at least 100 points on, and then you have to have actually a sigma, which is at the level of 100 micron. If you plug in the numbers, you see again what you want. No, so to summarize, you have to be large, precise, and light. And again, I'm afraid, even if I'm a silicon guy, that there is nothing else than a 3D gas detector imager that you have to consider. Now, the time projection is, of course, the baseline. We know there's a lot of experience, both in large system and in high-performance system. We know that a lot has been done for the ILD. We know that this is possibly not the only way out, and there might be other solutions that are very, very appealing. And what we are considering here is the drift chamber. It's a drift chamber that is, say, an evolution of what has been done for Chloe initially in Frascati, and then for the Mach 2 chamber. And the Mach 2 chamber has good numbers, and you will see how you have to scale them up. So it has been constructed, actually, and here are a few references. The Mach 2 is about 2 meters long, and it stops at 30 centimeters, so it's rather compact. And you have something like 10 layers, and the modularity is 30 degrees. If you want to fit it into a detector for this AEPC, you really have to scale it up significantly. So in terms of length, it's a factor 2, but you see it's nearly a factor 7 in terms of dimensions of the outer layer. So again, it's not going to be a piece of cake, but it might be interesting. So here it's providing you at least 112 points per track, possibly for inclined tracks a little bit more, which is not bad. And we know that actually in the construction itself, obviously, if you want to have the 3D, you have to have the U and V projection. And so you have, for instance, to string the wire between the spokes here that are not at the same azimuth. This is something that you can do. But we also know that actually if you want to have a good stability against electrostatic forces, you have to pull the wires with a strength which is about 25 grams each, and these are 40 micron diameter for the sense wires, and the total load is about 7.7 tons, which is not a piece of cake. Huh? And so again, what you want is actually, again, for instance, to decouple the mechanical support that you have for the wires from the gas envelope that you have. So if you go for such a design, then there are some advantages that you may consider. First, it's pretty light, and we know the being light is interesting. So the estimation is that you have 1.6% X0 in the barrel compared to something which is at the level of 8%, if I got the number right. And then even when you consider the end plates and the support, you're not exceeding 5% in the end plate, so in the forward and backward direction. Then again, it's interesting because if you are able actually to sample the signal waveform, and you will see this is one of my concerns, with a very high sampling rate, you will be able actually to see the signals which is associated to the different clusters in the ionization along the track. And then you will be able really to reconstruct and to overcome the biases that are associated to the reconstruction of the drift time, which is very interesting, but again, it's very demanding in terms of electronics, absolutely demanding. Now, if you manage to do so, then you can get up to an R5 resolution at 100 micron, which is pretty much comparable to the TPC. And again, in Z, you are at the level of 1 millimeter by the wire crossing, because actually the resistive charge separation at the two ends of the string is not giving you too much. The other good point is that, again, this is something I like. I mean, rather than doing particle identification by looking at the dE over dx, that we know it works, but we know that there, the distribution we have to cope with is the Landau distribution, and you have tails, so you have to use the truncated mean, which is something that we know how to do that, but by the end of the day is reducing the number of samples that you have. There, you go from the analog information to the digital information. So rather than looking at the amplitude of the cluster in the ionization, you look at the number. And then it's the Poisson distribution that enters the game, which is definitely easier for this number of samples to handle because it's pretty Gaussian with respect to the highly asymmetric Landau distribution. And again, for the same characteristics, the number of samples, here the estimate is that you go in a resolution of 4% to 2%. What does it mean? This is the particle ID, and this is done for the dE over dx, and this is done for the cluster counting. And you see that actually for every specific momentum and every particle separation that you consider, the fact that the Poisson is working better than the truncated mean over dE over dx is clearly evident. So again, this for me is a good advantage of this technology. Then again, something that was mentioned also yesterday, again, you have to make sure that when you run a Z, the TPC will stand the high particle flux that you have. So again, the Mach 2 prototype has been successfully tested up to a rate of 100 kilos per centimeter square, which is not bad. And the simulation are telling us that also through all the range of energies that we will be considering, the drift chamber shall not have any problem. Now, what do I see actually as a big question mark here? Is that, as I said, you have to sample the waveform at 5 gigasamples per second. So, which for everybody who knows works with digitizers, you know, is not a piece of cake. And again, you have to do it in such a way that the numbers are crunched in real time. Because if you want to really push on your equipment computer all of the data, then you need an optolink at 1 terabit per second that we know is not going to work. So the big challenge here, apart from the mechanics, apart, say, from the 7.7 tons, is that on the electronic side, you know that actually you have to be very clever and fast and low power consuming. Now, for calorimetry, again, here I will not belong because we know that actually the blue plot is not a Picasso, but we know is as famous in our community as a Picasso painting, and we know what it means. We know that we have to get there. And we also know that actually there is a nice solution for the particle flow. We know, and again, Monchi has been stressing the point, and everybody knows that it's going to work. But we also know that this is a bloody monster calorimeter. So it's not a piece of cake, really, to be able to handle. Originally, this is when it was in full glory, we had only for the ECAL 250 million pixels. I'm a pixel guy. I know what it means to keep it under control. It's definitely not trivial. Again, Jean-Claude Briand, we have been discussing at length. We know that actually now the pads are not the pixels, and we know also the assembly is easier, but again, we're talking about calorimetry, so every fluctuation does matter. Now, the question is, okay, this is a beautiful image. Can we do something different? We think we can, because again, calorimetry is not an imitation game. It's a fluctuation game. And we know that actually the share of the deposited energy between the electromagnetic component and the hadronic component plays a role. And we know that actually either you're compensating or you're measuring directly the fraction of the electromagnetic energy. Then you can do a lot better than being ignorant about that. And we know this has been exploited in the dual result concept, where you know that actually if you are sampling and you're measuring the Cherenkov light produced in any radiator and then the scintillation light, we know that the first one is more sensitive than the other to the electromagnetic component, and so you have actually the possibility to single out, event by event, the fraction of the electromagnetic component. And we have at least of 3 presentations today in the other session that is running soon after this one. They're telling you the principle, the simulation that we have, and the beam test result that we have got. So again, even if you're very conservative, you see that actually you can get up, and this was tracking back to the Sparkle Sparkle prototype, to the 30% over square root t, and also in terms of electromagnetic resolution is very close to what you need. So again, it's interesting. And we know that actually the dream, this is the name of the collaboration, was turned into a nightmare once we had to take into account that all of the fibers there had to be routed to the photomultipliers that, again, were in principle preventing you from engineering a detector that could fit into an experiment. But what we did over the past 2 years was actually to go away from the PMT and to enter into the silicon age. So we replaced the photodetector, the PMT, with photodetectors based on silicon photomultipliers. We had a tiny, small module that was essentially 1 square centimeters, but it was instrumented with 64 fibers, 32 Cherenkov and 32 scintillators. We had it on beam. We know that actually details will be in Santoro's talk, but we know that actually we did apparently well, and we proved that this is possible. This is just a couple of showers, centered and off-centers. This is a muon detector. We know that there are issues related to the residual crosstalk between the Cherenkov fibers and the scintillating fibers. We know that there's a lot to do in terms of optimizing the dynamic range. But we know that actually this is possible. And once you have it, then the possibility to integrate it into a full pi detector becomes real. OK, we had also a little bit of simulation. This is a bit, OK, we are late, but we know it's on the way. And the results are proving, then again, the targets can be met. Now, there are also detectors, and I'm close to the end, where the size matters more than the resolution. And again, this is when you have to keep large areas. So if you go actually to the pre-shower, if you go to the muons, there you have large areas that you need a modest granularity. And there, again, you're going away from silicon. You know that you have to go into something which is cheap, that can be industrialized. You go into the micro-pattern gas detectors. And we know you have the GEM, you know you have the micromegas, you have a lot of possible, say, declination of the MPGD. But we also know that there is now, again, it's an Italian project, you have the possibility to do something that apparently can be interesting, especially because a very limited cost can be industrialized. And this is called the micro-resistor well, which is in principle very easy because you have a pattern Kapton foil, and this is the multiplication region. And then you decouple, but in a capacitive way through, it's not capacitive coupling, but you have a high resistivity layer in between, which is dumping the stream that might occur, so it's spark protecting, and then it's also evacuating the charge which is collected. And so again, once you manage in an industrial way to pattern by lithography the Kapton, to then sputter the high resistivity layer, and then to glue this to a standard PCB that has the electron readout, you can have something interesting, and you can have something which is very, very low cost. This has been tested, and this has been proving that you can stand very high gains, up to 10 to the 4, where if you go, for instance, to gems, you have to consider the triple-state gems to prevent sparking. And we know that actually you can get up, this is a function of the resistivity, to levels where you have something at the level of 60 to 100 micron resolution per point, which is not bad, again. The time resolution is still, I mean, I've been listening to Munch, something where you have to improve, but again. Okay, and it has been hybridized in square meters. And now, again, I told you all of the pieces, and we can assemble the detector and finish the exercise, and I'm roughly on time. So you start with the beam pipe, you add the vertex detector, you add the radii, and again here, see, be brave. Don't stop at the original radius that I told you. Push it a little bit further. This so will be a big Coke can, but again, you can also relax the resolution requested you have to 5 microns. So it's interesting. Add the drift chambers, add the outer silicon layer just to have a better, say, acceptance definition. Add the superconducting coil, 2 Tesla, but very, very thin. Then add a pre-shower, add the dual readout calorimeter, the yoke and the Moore chambers, and voila, you got it. And we know that actually is a long way to go, but time is on our side. And I hope we will have people working with us. Thank you very much.
Thank you very much. Thank you for staying on time. I'm pushing because every minute counts. So questions?
I was not too late.
No. Questions, Macho?
So I think the DDX measurement using the cluster counting is a very efficient method. But I mean, at the electronic side, how are you going to separate the clusters from clusters? Using time measurement. So yeah, this,
By
I mean,
timing.
that's so you actually
yes.
already have the time information. So
you have the time information because you're sampling the waveform.
Yes. So
you can count exactly the clusters. So of course, it's Poissonian distributed. Yeah. So you have to be careful because, of course, the resolution is telling you how far apart in time they have to be.
Yeah.
But if you have a 5 gigasample per second digitizer, trust me, you can do a lot.
So actually, you already measured the time when you are doing the cluster counting. So I was just wondering if you can use some combination method offline and then simultaneously you also have the time of flight measurement.
I think so. I think so.
That would be quite cute.
Oh, yes.
Yes.
Oh, yes.
Yeah. And well, a tiny correction. I think the TPC material itself is not 8% X0. That's everything.
I apologize. I just got the numbers wrong.
Okay. Any other questions? I see another one.
Just curious. So your magnetic field here is 2 Tesla and yours was 3?
It's 2 Tesla.
Yeah. Is there some optimization of the magnetic field? What?
Yes.
Yeah, sorry.
So, I mean, that the optimization is with respect to what kinds of physics object, what kinds of measurements. Okay. Yeah, so then in the tracking, of course, that is just scale SB. But for the jet, we find it's not that sensitive. Basically, we get similar to 3, 3.5 and higher, but we do see a degradation when we move to the smaller, but not very significant. But on the other hand, I think the constraint is mainly from the high luminosity to the Z-pole to see that how many emittance blow up you will experience when your bunch coming through the solenoid. So I think that the key point is that if you really want to reach very, very high luminosity at the Z-pole, the low B magnetic field is welcome. But certainly the high B is always almost in every physics object, but not that significant.
Yeah, but you're talking about the machine interface, right?
Yeah, yeah.
No, I was talking about the physics measurements. So do we need such a high magnetic field to do these kind of measurements?
Well, if you want to keep it, compact, and if you want to have a decent Higgs to mu and even the recall mass measurement, you need it. Otherwise,
it's improving the separation anyway.
Yeah. Also.
If you can have it, it's improving the separation. So he can tell much better than I do the impact on the physics analysis, but I can tell on the detector side, of course, if I can have 3 Tesla, I will buy 3 Tesla.
Yeah, but you sweep away all your low PT stuff, right? So that's something you have to look at.
Yeah. Yes.
But how low is
For
low?
jets, I'm sure that's not great.
Yeah.
Yeah.
Well,
Okay.
it's all particle flow based, so sweeping things away is not an issue. You're starting from the original angles and position.
No, but I mean, you can't. I mean, at some low PT, you can't really reconstruct the track because you don't get the hits.
How low is low?
Well, that's maybe 100, 200, 300 MeV. I don't know. It depends how. Yeah, but you need 3. You know.
Yes.
Yeah.
You generate loopers, so yeah.
Yeah, no. But if you don't get at least 3 hits, you're never going to see
Oh, no,
anything.
I know. No. I think the 3-hit limit is much below. What they're talking about.
Yeah.
Yes.
No,
Yes.
no. Well, for CMS, we have 4 Tesla, and we don't go below 300, right?
Well, but we're sitting at 16
It's a different.
millimeter.
Yeah. It's much closer.
What is the
It's
radius?
closer. The
Yes.
third radius is going to be closer.
Yes.
Okay,
Yeah.
but I mean, still, you get a lot of combinatorial and everything. You're not going to do a decent tracking with that PT. And when you look at Z decays, you have lots of tracks which have 100 MeV PT. And so I don't know. Maybe you should check anyhow.
Well, yeah, I mean, it's an optimization. Certainly in this case, we will redo it then once we have again the full simulation for all these type of details. But
I mean, lab
I agree with
detectors
you.
could
Yes.
reconstruct
It's lower.
tracks
Yes.
at 50.
Yes.
So
and then the
Part of the optimization is also sweeping out of the background, because
It's-
if you
it's a
reduce,
machine, yeah.
if you reduce the machine, if you reduce the magnetic field of the solenoid, then you're also getting more background in your tracking
So
system.
as I said,
so it's a tricky business.
Yes.
You really have to do an optimization. Yes.
As I said, of course, knowing the number of hits per centimeter square per beam crossover is important, but unless I get the momentum, the spectrum of the momentum, then it will not be easy. Because as Franco said, if I have most of these that are actually looping into the innermost layer of the vertex detector, then I feel uneasy. So again, it's a part of the optimization. But also for me, a key point would be really to have a solid, with a good safety margin simulation of the background. This is
exactly
essential
Yes.
for me.
So